Hi, my name is Jun Wang, a Senior Field Application Scientist at Polymers. In this presentation, I will be discussing the theories and applications of DSC and TGA for polymer characterization. So what is polymer? A polymer is a large molecule or macromolecule composed of many repeated subunits. But let's forget the boring definition for a second and talk about what it really means to you. To kids, polymer could just mean city buddy on your coffee table or the cover case of their electronic devices. To everyday grocery shoppers, it may mean water bottles or the material used in an N95 mask. To Elon Musk, the whole universe is probably a polymer composed of many repeated galaxies. And don't forget his Tesla Roadster, made mostly with polymers, still flying up there. If you are a material scientist or an engineer, you are more interested in the science behind it, making new polymers or finding new ways of using polymers. Your daily job is to deal with all the issues in manufacturing and processing polymers, raw materials and parts or final products, QA, QC, failure analysis. All these are centered around a polymer characterization. From time to time, you may be looking at a material data sheet like this one and ask yourself, how do you measure these properties? Well, that's today's topic, how to characterize polymers using thermal analysis tools such as DSC and TGA. Let's have a quick overview of what thermal analysis is. Thermal analysis is a group of analytical techniques that measure the physical and chemical properties of a material as a function of temperature, time, or other conditions. The temperature range can go from liquid nitrogen temperature to over 2000 degrees C, so we are swinging between very hot and very cold temperatures. There's a lot of physical chemistry involved, like energy, enthalpy, heat capacity, sometimes chemical reactions as well, such as polymer curing, cross-linking reactions. There are 4 types of techniques commonly used. DSC measures the energy change. TGA measures the weight change. TMA gives you the modulus and dampening capability. And TMA usually measures the dimensional changes. The commonly used temperature profiles are depicted in the right graph. Heating or cooling at a constant rate, like the red curve, or held constant at a elevated or cold temperature, we call it isothermal temperatures, or cool heat cycles like the yellow curve, or any profile you want. Those physical properties can also be studied as you vary other conditions, such as relative humidity, UV intensity, purge gas change, etc., usually at a constant temperature. Now let's start with the DSC. There are 2 types of DSCs, heat flux DSC and power compensation DSC. Heat flux DSC uses a single furnace with a single heating source. You put a sample, usually in a sample pan, and a reference, usually an empty pan, in the pan holders inside the DSC furnace. As you heat the furnace, both sample temperature and the reference temperature are measured. The difference between the two, or delta T, is used to calculate the heat flow. The diagram shows a delay of the sample temperature, the TS in green curve. And that's a typical melting transition. This type of DSC used to be called Boltzmann DTA, and again, the heat flow is calculated. The other type of DSC is power compensation double furnace DSC. Compared to the heat flux DSC, the furnace mass is very small and much smaller, and each furnace has its own heaters and platinum temperature sensors. These furnaces are both heated at a pre-programmed heating or cooling rate, and the power compensations are applied to either furnace as required to maintain this rate. In the resulting DSC trace, the difference in energy flowing into the sample furnace is compared to the inner reference and plotted as a function of temperature or time. This design measures the flow of energy directly in milliwatts or joules per second directly and more accurately. The small furnaces of the system can be heated or cooled at very high rates. So this is fundamental of fast Scan DSC capability, which will be discussed in details later. What you see on this slide is a typical DSC thermogram consisting of a heating curve and a cooling curve. It's important to define the heat flow directions. As you see on the left, we usually use endo up, axle down notation, meaning upward peak is endothermic and the transitions absorbs heat when it occurs. Downward peak is exothermic. The transition releases heat as it happens. Different DSC software has different default settings, so you have to keep that in mind. From the heating curve, the first thing you see is probably a glass transition. Most people call it TG or T sub G. TG is from the amorphous content of a material. It tells you a lot about the polymer, and it's one of the most measured properties with the DSC. The second event is a cold crystallization. It's often seen from certain polymers like PET, PLLA, but not in every polymer. It occurs during slow heating when amorphous material is heated through its glass transition temperature and is able to recrystallize. This adds the degree of crystallinity, so its enthalpy change has to be subtracted from the melting peak later to calculate the degree of crystallinity as received. The cold crystallization can also overlap with the TG to make the TG hard to measure. This type of crystallization is different from the common crystallization from hot melt state, so as it termed cold crystallization. Other possible causes of a exothermic transition in this range above TG can be curing reactions and oxidation. The third one is usually a melting peak. The peak temperature is often called the TM. It is when the crystalline structure is destroyed by heat. It also may be solid-solid phase transitions, protein denaturation, which is also called TM, but it's really just the loss of the 3D structure of protein or peptides. The melting peak can be used to calculate percentage of a crystallinity. The long tail before the onset can also be used to calculate purity of an organic compound. The whole heating curve, when obtained using the proper method, can give you the specific heat as a function of temperature, useful to determine thermal diffusivity, etc. On the cooling curve, we often look at the crystallization. The onset temperature, heat of fusion are good indicators of polymer qualities. Melting is a first-order transition because it has a discontinuous step in the first-order derivative of the Gibbs free energy equation. For a small number of polymers, the heat of fusion of melting 100% crystalline is available. So if you are analyzing one of those polymers, degree of crystallinity can be calculated by comparing the delta H values using this equation. So taking HTPE as an example, the percentage crystallinity of this sample is 191 over 293, you get 65.3%. If the delta H value for 100% crystalline is not available for your polymer, you won't be able to get the absolute degree of percentage of crystallinity. You can still compare crystallinity between two similar materials. So what affects the TM? First, as you can see from this, the melting temperature for low density polyethylene is lower than high density polyethylene. TM further drops when the molecular weight decreases. So this is actually also a good reason why you need a DSC when your FTIR fails to give you the differences between these polyethylene samples, which have the same functional groups. Other than molecular weight, molecular structure, purity also affect TM. Plasticizers and contamination usually adds defects in the polymer crystalline structure and shifts the melting onset to a lower temperature. Crystallization can also be done isothermally. We have two raw material samples for packaging products. One is normal, but the other one is brittle. You can measure the melting to get the crystallinity because we know high crystallinity tends to make the material more brittle. You can also look at the isothermal crystallization behavior. First, you melt the samples and then cool them down to a temperature below Tm. As you can see from the top graph, the good material crystallizes slowly and ends up with a small delta H, indicating less crystallinity, whereas the bad one form more crystals in a much shorter period of time. The key to successfully capture full crystallization is to cool the sample as quickly as possible. The bottom graph shows that quench cooling gives you the full crystallization in the purple curve. The blue curve, however, is too slow and almost half of the material has crystallized before the set temperature is reached, giving you the wrong results. You may not be able to see any differences in the FTIR measurements, so what is causing all this? Molecular weight may have changed due to degradation from heat or UV radiation, or due to addition of dirty recyclates. The isothermal crystallization offers a great method for this type of test, especially when you have fast Scan DSC capability. TG is the second order transition because the first derivative of the Gibbs free energy is continuous, but the second order derivative is not continuous. TG is the temperature assigned to a region above which amorphous non-crystalline materials are fluid and rubbery, and below which they are immobile and rigid, simply frozen in a disordered non-crystalline state. When the polymer material is heated to this temperature region, the molecules start to gain enough energy and mobility. On a DSC curve, it shows a step change. Again, this is endo up, so what you see here is a step up. TG is a step change of the heat capacity, so the step size, or delta Cp, can be used to compare the amount of amorphous content between similar samples. Higher delta Cp means higher amorphous content. Sometimes a peak can occur on top of the glass transition, which can affect the calculation of TG. The red curve is the one we saw on the earlier slide. The blue and green curve obviously have a peak or overshoot on top of TG. They can be large enough to make it look nothing like a TG. Usually a large peak is due to relaxation of mechanically induced stresses resulting from the production of materials such as films or fibers, where the mechanical pulling is used to orient molecules in one particular direction. A common practice is to heat the sample passing melting, which will allow the stressed molecules to be able to rearrange. And the reheated sample after cooling will show a normal TG without the peak, like the red curve. Enthalpic relaxation usually gives rise to smaller peaks. It is often a result when heating a material which has been cooled slowly through TG or held just below the TG for a period of time. In other words, it has a thermal history. The previous slow cooling or annealing relaxed the material into a lower enthalpic state, as you can see from the left graph. Starting from the upper right down the line to lower left, slow cooling allows the material to take an early exit to the left. Isothermally or annealed just below TG, a material can relax into a lower energy state, as indicated. Heating annealed material at normal heating rate is likely to produce a slight overshoot of the true TG onset. Like the stress relaxation, enthalpy relaxation can also be removed using a heat-cool reheat method. The glass transition temperature is influenced by many factors. Polymers with bigger and longer molecules or more side groups, more cross-linked segments have higher TGs because of the lower mobility. Additives such as plasticizers can significantly lower the TG, and that's exactly the point of using a plasticizer. Plasticizers are generally lower molecule organic compounds, and they can soften rigid polymers to make them easier to process. Moisture is a special kind of plasticizer. Sometimes it's not wanted though. For example, in the pharmaceutical industry, moisture can lead to the loss of strength and stability of API, so storing your medication in the bathroom cabinet is not really a good idea. Sometimes you need to make copolymers or blends. TG will tell you if the polymers are miscible or not. Miscible copolymers have a new TG somewhere between the individual TGs. TG is different when you are not using the same method or conditions. These two graphs show you that the heating rate can affect the TG measurement of some polymers, especially when the heating rate is higher than 100 degrees C per minute. We already know cooling rate, annealing, and storage temperature affect TG. TG can also be measured by other techniques such as DMA and TMA. The results can be very different because they're measuring different properties. Even if you are using DSC exactly the same way, the results can still be different if you assign them in another way. For example, you can get onset and effective temperature inflection point or half CP extrapolated. You have to report the method you use to calculate the TG, otherwise the results won't match. Most users use half CP extrapolated and sometimes include the onset as well. Again, TG is not a single point, it's a temperature range. Quickly, let me show you an example of using DSC to determine the degree of cure. When you have a partially cured sample like this composite material, you want to heat it first to temperature when the residual cure is complete. And with this, you can calculate the residual cure and possible TG as well, because TG is a function of degree of cure too. Cool it down and reheat it. You'll get the TG of the fully cured sample as shown in the green curve. You would also need to have the uncured liquid resin and use the same method to calculate the maximum delta H. With the two delta H values we obtained, the percentage cure can be easily calculated using this equation. If you don't have the uncured resin, you can still compare the percentage cure of partially cured samples by looking at the residual cure. Another common DSC application is measuring specific heat as a function of temperature over a wide temperature range. The textbook method is the so-called three-curve method. An ISO, heat ISO, temperature program is used, as shown in the black curve on the left. The same scan is applied to the empty furnace as a baseline, a sapphire standard, normally a thin disk, and a sample made into a similar shape as the sapphire disk. The CP can be calculated using this equation on the top right. By using this method, we get the CP for each temperature, useful to calculate the thermal diffusivity, etc. And also we can use it to separate overlapping transitions. StepScan is based on the specific heat method, and it's an alternative way to modulate the temperature DSC. A lot of you may have heard or used the modulated DSC to separate reversing and non-reversing events. StepScan works for the same purpose, oftentimes produces quicker and better results. The blue curve is the temperature program consisting of multiple ISO, heat ISO steps. The red curve is the actual heat flow data when you run a sample using the temperature steps. For each step, you can get the CP, and when the end of each isothermal step is connected, it's a line called ISO-K. This is an example of StepScan of PET sample. Basically, the blue CP curve carries all the fast and thermodynamically controlled transitions like TG and TM. They are reversible. The red ISO-K curve shows the slow, non-reversible, kinetically controlled events such as the overshoot on top of a TG and the cold crystallization as indicated in the second red circle. StepScan not only produces the accurate measurement of CP, but also separates out transitions of different natures, which are often overlapping. This is very helpful to accurately measure the TG and TM. Let's look at some examples using the StepScan. Top left is a pigment sample run at 10 degrees C per minute. Two big bumps with no TG inside. When you run the same sample with the StepScan, bottom left, those bumps are moved to the ISO-K baseline, and TG can be clearly identified in the CP curve. Graph on the right is a polymer blend. Three distinctive TGs are found without the interference of thermal history or cold crystallization. If you still remember what I mentioned earlier, you know this is absolutely a blend, not a miscible copolymer, because the TG of all three polymers still exist. I'm not sure if anyone from the audience today needs to measure oxidative stability. You can easily do so with the DSC. All you have to do is add a second purge gas line to the DSC. Program the software to switch gas from nitrogen to oxygen at an elevated temperature to capture the oxidation time. There is a ASTM method for this OIT test. This example shows the significant difference of oxidative stability between the new motor oil and used oil. This method can be used on polymers too. I have mentioned some advantages of fast scans, such as quench cooling for isothermal crystallization. Fast scan is only possible with the small furnaces like the ones using the power compensation DSC. We have a vague definition of fast scan rate. We will just say here 300 degrees C per minute or higher would provide the significant advantage of fast scan features compared to 10 or 20 degrees C per minute traditional scan rates you use every day. We all know that the heat flow from the DSC is determined by three variables: CP, sample mass, and scan rate. We want higher sensitivity. We want to be able to detect very weak transitions caused by, for example, the side chain movement. We cannot change the CP because it's intrinsic to the sample. We can use bigger samples, but there is a limit, and you are also increasing the thermal lag across the samples. Of course, we can always try to make the baseline flatter, but there will be noise. So it seems increasing the scan rate is more practical, and it brings the largest improvement on the signal. You can also see the weak glass transition being measured with fast scan rate here, which is not seen in a traditional slow run. With fast scan rates, you also get additional benefits. You can get results much faster, like in this one, 30 minutes versus less than a minute. Let's take a look at some applications where fast scan is used. First one, sometimes we don't have enough sample to run. In this case, only 0.07 milligrams of sample is available, but we want to know the TG. Or in this case, an artificial knee is used for 2 years and it's causing issues like friction. We can only take a tiny piece out of the patient for analysis. You can see the material is more crystallized after 2 years of use. Or we know polyethylene has a very weak TG below negative 100 degrees C. It's easy with the fast scans. We talked about cold crystallization, commonly seen with the slow scans in the blue curve. StepScan can separate it out, but it's a very slow run. Fast scan can suppress it in a much shorter run and produces the correct crystallinity without addition from the cold crystallization. If you need to measure TG of an uncured or partially cured sample, the residual cure oftentimes gets in the way. With fast scan, you can suppress or delay the residual cure to have a clearer TG before the curing exotherm. Another example is moving a water evaporation peak off from the TG. See the huge difference between 10 degrees C per minute black curve and the 500 degrees C per minute red curve. The last example of fast scan shows you the delay of decomposition, which sometimes occurs during a polymer melting transition. All you can see from the slow 90-degree run is the decomposition peak. Whereas when you speed up the scan, you can push the decomposition off and review the two small melting events on the red curve. The TG also becomes more pronounced. The next DSC application has to do with using UV radiation to cure a resin and how to calculate the percentage cure. Dual furnace DSC is also preferred because the UV light on top of the exothermic reaction can heat the sample up to a much higher temperature than the set temperature. The power compensation design can quickly remove the additional heat and provide true isothermal curing. This is an example. This is a simple method. You turn on the UV 2 times in a single run, one for curing and the second time to get a baseline. After subtracting the baseline from the first part of the curve, accurate curing profile and the percentage cure are obtained. Then you can satisfy your other curiosity, like how the UV intensity and other conditions affect the curing. The top graph shows the peak time is shortened and the shape changes as you increase the UV intensity. The bottom one is where you vary the isothermal temperatures and seeing similar effects on the curing profile. With all these information, one can easily and quickly optimize the processing conditions. The next popular use of the DSC is kinetic analysis. It's another powerful tool for the study of curing, crystallization, or other reaction mechanism. Some users are actually doing this every day to predict the reactions under extreme conditions. Those conditions are either too hard to realize or taking too long to finish a test. You can normally do this in two ways. One is done isothermally at a series of temperatures. For example, curing a sample at 40, 45, 50, 60 degrees C. The other is to run the samples at various heating rates. In both cases, the peak area is integrated for kinetic analysis. The Arrhenius equation is used in the calculation of the rate of reaction, but there are two different approaches when it comes to whether or not a mathematical reaction model is used. In the first approach, you have to choose a reaction model, nth order or autocatalytic. The model equations are listed here. The other method is called model-free kinetics. If you rearrange the rate of the reaction equation and integrate it, the activation energy in the Arrhenius equation, or simply put it, the energy barrier, is not a constant anymore. It is now a function of the extent of conversion. This eliminates the need for assumption of a certain reaction model and make it possible to obtain the apparent activation energy. This is a more sophisticated approach, and one can possibly relate the changing activation energy to condensed phase reaction phenomena such as diffusion, nucleation, and growth as a function of the extent of conversion. It provides more insight into the reaction mechanism. Either approach allows one to make kinetic predictions. The top plot is the prediction of crystallization at higher temperatures based on low temperature data. Look at the orange curve, the time it takes to crystallize at 125 degrees C. It would take too long to actually run a sample at this temperature. Kinetic analysis saves time. You can also predict the percentage of crystallinity at other linear cooling rates, as shown in the lower graph. The same method can be used in curing analysis. It helps design or optimization of processing conditions, such as the current temperature, time, etc. This saves both time and cost. We have covered a lot of DSC applications. That's not all for sure, but maybe enough to get you more interested in it. Now the question is, I have a DSC, how do I get good results with it? Or how do I interpret the data? In the next 3 slides, we will discuss what it takes to get good results. First, you have to choose the proper pens. There are all kinds of pens of different materials, shapes, and volume. The most commonly used pens are aluminum pens, usually with a lid. They're good for most of your solid samples, powder, film, pellets. If you have samples with volatile ingredients, then you have to know how high the temperature you're going to go. For low or moderately high temperatures, you want to use hermetically sealed pens, which will be sealed airtight to keep the volatiles. There are special pens like the one on the right. They can hold pressures up to 150 bars. Otherwise, you can just pick a vented pen, where there is a tiny pinhole on the top of the lid to help relieve internal pressure while keep most of the volatiles inside. If you are heating above 600 degrees C or your material reacts with aluminum, you need to pick a different material like ceramic, platinum, gold, stainless steel. Aluminum pans will melt and stick to the furnace for good if you heat it past 600 degrees C. Next, prepare the sample properly. There are many techniques and tricks, cutting, sanding, just to name a few. An ideal DSC sample should have good contact with the pan for better heat conduction. After crimping or sealing, always check the bottom and make sure it's flat. Set up the temperature program in a way that it starts at least 20 degrees below the first transition to allow the DSC signal finish the initial transient. You don't want to heat the sample beyond its decomposition temperature, otherwise you have to clean the furnace very often. Run a TGA first to find out the onset temperature of decomposition if you have one. Then you stop the temperature there in a DSC run. A typical scan rate is 20 degrees C per minute for TG and 10 degrees C per minute for melting temperatures. Use slower or faster scan rates when you have sample size issues or you want to explore the fast scan capabilities. Numerous ASTM methods require standard heat, cool, reheat measurement to eliminate thermal history. This is an example showing you how the reheat data, blue curve, is better suited for TG analysis after the thermal history or moisture is removed. Sample size 5 to 10 milligrams, typical for polymer samples. Use smaller ones for fast scans. Purge gas has to be used, and it must be dry because the subambient cooling device is usually required, and we don't want the DSC furnace to be filled with frost. And helium is recommended if temperature is lower than negative 100 degrees C. This is where nitrogen becomes sticky and a poor heat dissipator. Regular calibration is often neglected, but it's critical for getting accurate data. Even if the DSC is well maintained, you need to recalibrate it after you have changed the cooling device, purge gas, type of pens, and last but not least, scan rates. Always have your indium or zinc standard ready for a quick check of performance. Most users have plus minus half degree as the temperature tolerance and 1% for delta H acceptance criteria. Data analysis and the interpretation is often complicated and can be very challenging to beginners. It takes some formal training and practice to master. Here's a couple of pointers. To calculate the melting peak area, the baseline needs to be selected according to the peak characteristics. The one on the left doesn't have a baseline shift, so you can just use a straight line. The one on the right has a shift due to the significant increase of Cp after melting. This is where you want to use a sigmoidal type of a baseline. For isothermal tests, oftentimes you need to use the horizontal baseline. There's an option to choose baseline type in the DSC software. Another example, which I have mentioned earlier, is the calculation of crystallinity using the melting peak. Make sure you subtract the cold crystallization. This PET sample is sort of unique because the baseline is actually a straight line between TG and the melt. So you can just do crystallinity analysis in one action. This pretty much summarized the DSC topics, and we are switching gear to TGA. TGA is a much simpler technique, so I won't spend as much time on it, but it's a very powerful tool. There are three kinds of balance designs. First one is hand down or bottom loading, where the sample pan is hooked on a hand down wire from the balance on top. Second is top loading design. The sample is sitting on top of balance supported by a stem. There are also horizontal designs available. Hand down design usually offers the best sensitivity, as good as a tenth of a microgram. So where is TGA used? Anywhere the weight change due to the listed reasons here. This example shows the TGA analysis of a rubber material. You can see the weight loss due to evaporation of moisture, volatiles, oil exchanger, polymer decomposition in the inert nitrogen purge. When a gas is switched from nitrogen to oxygen, carbon is burned. There could be ash at the end from inorganic ingredients if there's any. I'm using a grease sample as a tricky one. It has multiple components and hard to separate using the standard linear heating rate. The first derivative, or DTG, is often used to display weight losses in peaks. As you can see here, 3 steps are identified, but we know this material is more complex than that. So how do we increase the resolution and expose more components? Here are a couple of options, auto stepwise and a variable rate scan. Both methods share the same idea, that is to slow down the heating to let one mass loss step finish before moving on to the next step. The difference is how to slow down the heating. With auto stepwise, the sample is heated at a constant rate. If a significant weight loss is detected, the sample is subject to isothermal conditions. In other words, it slows down to completely no heating. When the rate of the mass loss becomes very small, the program resumes heating the sample until the next significant weight loss step is encountered. Variable rate scan is more sophisticated. It calculates the desired heating rate in real time and adjusts gradually. The results: the variable rate scan works better for the grease sample. More weight loss steps are revealed. Corresponding peaks in the DTG curve are also displayed here. At least 8 ingredients can be calculated with this smart TGA method. Okay, we have talked about 2 individual techniques, DSC and TGA. Is there a way to combine them, like this helmet, but also a beer can holder? Modern thermal balances can be equipped so that they can record a DSC signal at the same time as the actual thermogravimetric measurement. It is a simultaneous TGA DSC, or STA. There are many different designs. I'm only showing 2. This is a cutaway design diagram in the middle of an STA instrument. The 2 designs are both top-loading TGA with additional PET ring or pen holder to serve as the reference, so the delta T can be measured at the same time when the mass change is recorded. The simultaneous analyzer not only allows one to run the exact same sample in one instrument, so the DSC and TGA data can be precisely overlaid, but also the information is complementary. This helps a lot in the interpretation of transitions. For example, if you look at the table, both the loss of volatiles and the melting are endothermic, appearing as a peak. They can only be easily differentiated with the weight change information. Melting does not have a weight loss. Another example, there's a weight loss from degradation and oxidation on the TGA curve. But degradation is endothermic while oxidation is exothermic. So 1 plus 1 is greater than 2. Using it to analyze a batch of copolymers with different compositions, the TGA data shows that the thermal stability is dramatically different among these samples. The material with higher percentage of ABS is more stable. DSC is used to quantify the composition by measuring the delta H of the acetal melting peak. As you can see, the calculated percentage of acetal is consistent with the actual percentage. The TG of ABS can be seen in a high ABS sample. With the last slide, I would like to briefly discuss the EGA analysis, evolved gas analysis. The percentage of weight loss from a TGA or STA can be calculated for any given weight loss event, which answers the question how much. However, TGA alone yields no information regarding what components are being decomposed. This information requires that we probe the chemistry of the evolved gases by transferring the gases to a secondary instrument. This can be a FTIR or mass spec or GC mass spec. A transfer line is needed not only to keep the gases hot, so no condensation along the transfer line, but also for precise control of the flow rate, which is critical for real-time analysis. Using FTIR, we probe the molecule structure based on the absorption bands of the different molecule bonds in the evolved gases. A 3D plot is available to show the real-time gas evolving as a function of temperature or time. You can even use principal component analysis to differentiate closely related materials. GC, gas chromatography, allows the separation of complex gas mixtures, and eventually the gases can be identified by mass spec using the libraries of mass fragmentation patterns from the parent molecules. All these additional information will give us a better understanding of complex materials and how they behave and interact at elevated temperatures. The hyphenated systems are extremely useful for the analysis of residual solvents, semi-volatiles, and decomposition processes. This concludes my presentation today. For more information, please visit PerkinElmer Thermal Analysis website or contact me directly. Thank you for attending this webinar.